So there was one a cone problem that is left. I think except that one I did solve rest of all. Okay. Before getting into that cone problem, we shall have a ring problem, all right? I have a ring. Okay. I have a ring of total charge Q, okay, of radius small r. Let me take radius small r. And what is the potential at a distance z above the center of the ring? Is that okay? Total charge is Q, uniformly distributed. So now you can take this one, elementary charge, isn't it? And this is dq. So this is italic r, isn't it? This is z, r here. This is origin, but actually this is r prime actually. Okay. From origin to source point is r prime actually. I written it according to our earlier notation, but I have taken it as r. I hope you are not worried with that one. Okay. Actually, this is the field point actually. Is that okay? Again, we are trying to find potential at this z. Am I right? That v at z is equal to, this is a scalar integral, 1 by 4 pi epsilon naught integral of dq divided by italic r. Is that it? Now again, if you sweep this dq, that italic r, it's a cone. Am I right? It will sweep a cone. So that's why that italic r is constant actually. You can take it outside, 1 by 4 pi epsilon naught 1 by italic r integral of dq. So when you sum all of this elementary charge, you will get total charge. So that's why potential at z, that's equal to 1 by 4 pi epsilon naught, okay, q by italic r. Is that okay? Speak out. Q by italic r. And what is that italic r? Italic r is equal to root of z square plus r square. Both z and r are constant here. Is that okay? Speak out. Integral of dq. Scalar integral. In case of electric field also we did similar, but we needed to do we needed to resolve that one. Am I right? That was the small difference, and we defined line charge density and all. Okay. But here I have taken total charge Q here. Is that okay? V at z, okay, that's equal to 1 by 4 pi epsilon naught, okay, Q by italic r. You should know what is this italic r, okay? What is this italic r? Keep this one in mind, or let me draw it here again. Is that okay? This is the situation. Now there is one problem. You have a cone, okay? Again, if you draw the diagram, I hope most part of the problem is almost solved, okay? If you draw the diagram properly. You have a cone like this, and you have point A here. I mean, with respect to some origin, you have another point B here. I think that cone is not appropriate because he has given one geometrical condition, okay? I think there's a problem about 2.26, okay? A conical surface. A conical surface. Okay. What he has given is this height is same as this radius, okay? This is A, this is B. This radius of this this planar part, that is same as this height. He has given h and h here. Is that okay? Speak out, anyone. Now I need to find potential at this point, and I need to find potential at this point. Okay, take infinity at the take this one only. Okay, I'll take this one, 1 by 4 pi epsilon naught integral of dq divided by italic r. I'll take this one because finite charge distribution. Look at here. This is an ice cream cone. Okay. This is an ice cream cone. There is no volume charge distribution. There is a surface charge distribution, sigma. Is that okay? That's a surface charge distribution. No charges, I think, on this one. Am I right? Anyone? Conical surface, an empty ice cream cone. Yeah, that's correct. Again, only surface charges exist in the curved surface. Is that okay? That is the situation. You need to find potential at this point, potential at this point. Finite charge distribution, take infinity at the reference point and find the potential difference. That's what he is asking. If I'm using this formula, means infinity is my reference point. Again, you can't find the electric field and then you can do that. It's very difficult, am I right? Is it possible to do this one using Gauss law, integral, electric field integral? I hope it's very difficult. Find the potential. If you take the gradient, you will get the, what you call, electric field actually. Is that okay? Now look at here. We shall, again, the target is to find the potential difference. Now to find that potential difference, okay, now look at here. What I do is to find potential at this point, okay, just like I found potential at this point, am I right? Now what I do is I'm going to divide this curved surface into a ring like that. But when I divide that ring look like this. Can you imagine? Is that okay? That ring will look like this actually. Can you see this part of the board? I mean, this color change or something? At least a little bit. When you draw it clearly, okay, when you draw it clearly, this ring look like this actually. You have to draw it very, very neatly, then I think you will solve this one, okay? Can I draw it like this? Now this is a ring. Let me take off radius r, okay? If it has a radius r, this height is also r, because this will be similar angle compared to this one. Can I write like this? I hope you can grab the geometry. This angle, okay, is similar to this angle, okay? This is h and this is h, okay? That's why this, if this is r, this should be r, okay? Now look at here. Now due to this ring is a portion of this whole surface, am I right? Due to ring, what is the potential at this one? Because this is a portion, am I right? So that's why this ring will produce a small amount of what you call potential at this point. I'll write dV at A. Is that okay? Due to this ring. So that's equal to 1 by 4 pi epsilon naught. I'm going to use this one. This formula. 1 by 4 pi epsilon naught. Now, charge on this ring, I'm going to take it as dq. Okay? dq divided by what is italic r? Italic r is this kind of distance. Am I right? Again, this is just inverted. That is this italic r. Am I right? Can I take like this? This is a italic r. To this point, speak out. dq by italic r. Actually, italic r is equal to root 2 into small r. Am I right? You can see that. Italic r is equal to root 2 into small r. Check this out. R root 2 into, am I right? Yes. So can I write like this? This diagram inverted. R here, Z here, this is italic R here. You are finding potential at this Z, okay? Can you just match these two? Now here this total ring have got charge Q, but here I have taken total ring have got charge dQ, because that is a portion of whole surface. Here that was the whole, that ring was the whole thing, whole charge, but here that's a portion of the total charge. That's why I have taken it as dq dv, because I need to integrate later, isn't it? Now how do you relate this dq to this sigma uniform surface charge density? That's a very tricky part. Is that okay? Now first to find the circumference of this, what you call this one, this dq. To find dq, first find the circumference. That's equal to 2 pi r. Am I right? Now if you write 2 pi r into dr, that would be wrong. Okay, if you write 2 pi r into dr, what you will get is, so this is 2 pi r. You are extending in the plane of this circle actually. That 2 pi r into dr, you are extending in that plane. Are you getting my point? But this surface is not extending in this plane. It is that is extending like this. Are you getting my point? Can you just grab this one? It is extending in this direction actually. Speak out. The surface is like this ribbon. So that's why 2 pi r into not dr, okay? If you write 2 pi r into dr, it will extend what you call in this plane. But again, 2 pi r circumference, it should be grabbed like this, okay? So that's why this is dr. We are going to take this one as a dr. This distance, right, we are going to take d italic r because this extension is along this italic r direction actually. 2 pi r into d italic r. If you grab this one, wait a second. So this is a surface area, okay? So this is a circumference. If you multiply by dr, 2 pi r into dr italic r, it will get the surface area. If you multiply by sigma, you will get a charge. If you grab this equation, I think it's almost done. I mean, problem is almost done. Speak out. I mean, sigma into dA, am I right? What is dA? dA is the surface area of this ring. But that ring, it is not what you call a kind of, it is spread over the plane, am I right? It is like this, am I right? Speak out. Let me draw it here again. It is like this. Speak out, anyone? Can you just imagine? So this is radius r, okay? So this is dr, that's what I have taken. Speak out. So that's why to write this dA, you have to write 2 pi r, this is circumference, into dr, 2 pi r into d italic r. If you grab this point, I think almost done. Later thing is to integrate. Yeah, speak out. Any question here? Can you grab the difference between these two? Whatever we have here, that is this one actually, not this one. I hope you. Now, this is a portion of a disc actually. This is a portion of a ring actually. A ring kind of thing. This is a portion of a disc actually. So that's why whatever we have here, again, if you substitute that one, that's equal to 1 by 4 pi epsilon naught in what you call sigma into 2 pi r d italic r divided by italic r, okay? Now you can just integrate that one, am I right? Scalar integral. To find potential at A, you can just integrate sigma by 4 pi epsilon naught. Sigma is constant, 2 pi is also constant, okay? Integral of r d italic r divided by italic r. Now you got two choice. One is you can run italic r from 0 to root 2h, am I right? You can write, you can convert either the whole thing into italic or r is also variable, italic r is also variable. Now using this equation, you can convert. If you convert it into r varies from 0 to h, am I right? When this ring is here, r equal to 0. When ring is here, r equal to h, okay? If you convert that one into italic r using this equation, italic r varies from 0 to root 2h. Is that okay? Italic r equal to 0 to root 2h. Again, that's your choice. Can you do that integral? Very simple integral. When you substitute, it will get cancelled. It's very on the range actually. Very simple integral. Is that okay? Speak out. That is potential at this point. Over? Now potential at B, that is not that straightforward, okay? Potential at B. I'll not do the integral, okay? I'll not do the integral. To find potential at B, again I need what you call, let me think like this. Let me think like this. I have a ring here. I have Z here. R. Okay. I have italic R here. Okay. Let me think like this. I have a ring here. If this is R, what is this one? Speak out. That doesn't matter. Okay. This doesn't matter. I need this distance. Am I right? I'll write italic R prime. That doesn't matter, am I right? That depends on italic R, not this distance. Later I will convert this R prime somehow. Is that okay? Speak out. Now, again, potential at B due to this elementary, that's equal to dV at B, that's equal to 1 by 4 phi epsilon naught, okay? So this whole thing have got charge dq ring, and this radius is r prime. Is that okay? Speak out. Again, what is dq? dq is again the exactly same, sigma into 2 pi r into d italic r, this italic r. Using this r prime, you can't write this surface area actually, this r prime, because this r prime varies like this. Can you just imagine over the surface? That's quite difficult. Okay, you can't write like this. You may need to define some angle here. That's very difficult. Okay, but this dq, it is related to this italic r. Is that okay? This dr, whatever I am writing, this is this italic r, but this whatever r that came, look at here, 1 by 4 phi epsilon naught, okay? dq is equal to sigma into 2 pi r into d italic r. So this divided by r prime. These two are different. This dr is related to this one. This is related to, this is different. Is that okay? Using this, don't write dr prime. dr prime is, again, if this is r prime, dr prime will be along this direction, isn't it? If this is r, dr will be along this direction. Okay, find the difference. Now we need relation between this r and r prime actually. I mean, we convert r prime into r, so that very easy to run r integral. Am I right? Speak out. Now to do that one, we do like this. From source point to field point, am I right? How do I take? Let me take one vector like this.
Sir?
Yes, speak out.
Sir, can we define an angle here between r prime vector and perpendicular?
R prime and?
Small angle between these two?
No. Look at here. Ultimately, again, r prime is required, but you better to convert that r prime into this r and this height again. That can be possible. Convert that one into earlier variable so that you can do the earlier limit, isn't it? Again, here defining this area using this r prime is too difficult. That's what I'm saying. You need some angle here.
Sir?
Yeah, speak out.
Sir, what if we convert both italic r and italic r prime into small r?
That can be done. Earlier also I told him, right? But r prime, how do you convert r prime into small r?
Sir, it will be under
H minus r. Okay. That's okay. This is h minus r. Am I right? Yeah, write it as root of r square h minus r the whole square. Am I right? Yeah, you can do that one. That's okay. That's very nice step actually. dr also in terms of r. You better to convert everything into that one. That's also okay. But what he has done is, okay, look at here. Again, because this kind of idea you better to generate actually. He defined one vector here, other vector here, okay? One vector here, other vector here. How do you write these two? Again, this one. How do you generate this vector now? Speak out. R minus R. Now let me write this vector, but ultimately I need a scalar. Okay, it doesn't matter what kind of vector you define. Okay.
Sir, by taking angle concept, we can do this.
So let me define one h vector here. Okay, and I know this angle. This angle is equal to 45 degree.
Yes, sir.
I know this angle. Wait a second. R prime vector is equal to R vector minus H vector. Check this out. Minus H vector, R vector. No. H vector minus R vector. Yeah. H vector minus R vector. Okay. Yeah. H vector minus R vector. Yeah, that's equal to R prime vector. Okay. Now this R prime, that's equal to, that's correct. Okay. Whatever he told, try that out. Okay. You can directly convert this R prime in terms of H. This is H minus R. This is R. This is H minus R. This is R. Okay. Just write that one and do that do in both way and try to compare. Okay. Equal to H square plus R square. Okay. Minus H and R angle is what you call cos 45 degree. So 2HR cos 45 degree 1 by root 2. So that's equal to root of H square plus R square minus root 2 HR. Substitute everything is in terms of d italic r and then do the integral. I think that is more lengthy, isn't it? So let me try whatever he told. If I can do that integral quickly. Again, that would be quite lengthy integral. Okay, you have to do the integral. Potential at B ultimately, that's equal to 1 by 4 phi epsilon naught. Okay, sigma into 2 phi, I think, integral. R d italic r you can convert, divided by root of H square plus R square minus root 2 HR. Isn't it? I think that is quite lengthy, this integral. As he told, let me try to convert this R prime, italic R prime, that's equal to root of H minus R the whole square plus R square. Check this out. What is this one? No, I think you will have similar integral. Okay, integral cannot be reduced. 2R square plus H square minus 2HR. Yeah, I think integral cannot be reduced. That root came in, isn't it? Again, R, dr. Anyway, you need to do some substitution and you need to do this integral. It will be some logarithmic. I hope hyperbolic kind of function will come that can be converted into logarithmic or R square into R. Am I right? I think if you take a derivative here, can you write like this derivative of something? Can you do? Yeah, this integral is quite lengthy. So after that you need to take the subtraction. Okay, once you do until this one later, again it's a work, you should work on that integral. Okay, is that okay? Speak out. I hope you got the logic of writing this one. This is very tricky step actually. And the similar step is followed in case of, suppose if you have a disk, if you found the electric field due to disk, how to find electric field due to a cylinder. If you have a, what do you call, electric field due to a ring, how do you find electric field due to a disk using a ring? Isn't it? You know the electric field due to a ring. How do you find electric field due to a disk? Using the, what do you call, electric field due to ring. You need to integrate, isn't it? Earlier idea. Exactly similar idea, but again, you should grab this side. Okay, very nice problem. I think problem 2.27 I gave hint already. I don't have to take care of that one. There is no electric field outside. Electric field discontinuity. Electric field inside is sigma by epsilon naught. Yeah, discontinuity is sigma by epsilon naught.
Yes, sir. But if I want to verify with the formula that E above magnitude
Wait, once again, let me draw first. Okay, so inside electric field is sigma by epsilon naught into along, suppose y cap. Okay, yeah, outside electric field is 0. Now tell me.
Now, if I consider the rightmost plate and if I write the E below sigma by epsilon,
I better take like this. Then only above below is more comfortable. Am I right? Yeah, let me take origin here. Okay. Now below electric field is 0. Above electric field is E is equal to sigma by epsilon naught y cap. Okay. Below electric field is 0. Outside electric field is 0. Then also. Below electric field is non-zero, above electric field is 0. Change in electric field sigma by epsilon naught.
But then if I vectorally consider, then it will be minus sigma by epsilon naught.
Wait, once again. So here, what we have written, E above dot n cap minus E below dot n cap is equal to, it should be sigma by epsilon naught, am I right? Now this is the surface, this is the surface we have taken, this is n cap, you are saying negative sign. No, that's correct, this has a negative charge density, this had a positive charge density, that's correct, isn't it? 3 2 positive charge QB are at rest, hold together, massless string of length A, stringy skirt, particles fly opposite direction. Now when again find the initial energy, initial potential energy, okay, is converted into kinetic energy. When they are very far away, potential energy is 0. Okay. Then convert that one into kinetic energy of each. Take velocity same to conserve the momentum also. Okay, when you cut that one, they move opposite direction with the equal velocity. They have same mass. No, masses M A and B. Okay, conserve momentum. Okay, M A V A is equal to M B V B. Okay, and then half M V A square plus half M V B square. That is the final kinetic energy. That's equal to initial potential energy of the system. Okay. Conservation of momentum and energy. Yeah, speak out. So then again, let me quickly explain this 2.50. I hope rest of things you can do. 2.50, that's equal to potential is given. Okay, potential is given, that's equal to, let me just give the hint. Okay, A e power minus lambda r divided by r. Okay, and he's asking what is the charge density and what is the total charge. What is the electric field, then what is the total charge? Electric field, okay, at r, that's equal to negative gradient of V. Speak out. That's equal to, it contains only r part of the derivative, am I right? That's why you can write like this, r cap, okay, negative dou by dou r of this one minus A e power minus lambda r divided by r. So can I write like this? How do you write gradient in case of, that's equal to r cap dou by dou r of V plus theta cap dou by dou theta, theta cap by r, I think, but there is no theta variable here. I hope this is the thing. Okay, when you do this one, I hope you will get r cap by r square multiplied with something. Check this out. Speak out. Anyone? E power minus lambda r 1 plus lambda r. You'll get this one. R cap by r square. Now take this one as a scalar, this one as a vector. Is that okay? Scalar into vector field. What is the, again, next thing is to find rho. Rho is equal to epsilon naught into divergence of electric field. Am I right? Speak out. Now, while doing that one, okay, while doing that one, you need to do divergence of scalar field into vector field. Am I right? Speak out. What is this one? Anyone? Scalar into divergence of vector field plus vector field dot product with gradient of that scalar field. Check this out. You should use this formula. Because at r equal to 0, you have a problem here, okay? R equal to 0, this is finite, okay? This is going infinity. If you take this formula, it will take care of everything actually. Del dot V, where what is V? This is the vector field actually. That is a, what you call, your Dirac delta. Del dot r cap by r square. 4 pi delta cube of r actually. Speak out. Gradient is also this gradient only.
E equals to minus del v, sir.
Denominator r square e power minus lambda r into.
I would say that.
No, this is right, I think. Check this out. R square 1 lambda. Yeah, that's correct. Negative sign will come. 2 negative sign will come. That is cancelled out with this one. Yeah, this is correct. Check this out.
I was getting wrong.
Check that out. Positive only. Now look at here. What you will get here is f into, what is f? A e power minus lambda r into 1 plus lambda r into divergence of this one, that's equal to 4 pi delta cube of r. So plus this one you can do. Again, you have to take gradient of this one. Okay, this is a scalar part. This is f, this is v. That's what I have taken. Now delta cube of r into this one. Okay, it will choose the function. Again, there is a property, am I right? Again, f of r into delta cube of what you call r minus a. I hope that's equal to f of a into delta cube of r minus a. Am I right? Anyone? Or later if you do the integration, the same thing will come. This kind of property, do you remember? We have used somewhere. Shall I write it here? F of x into delta of x minus a, that's equal to f of a into delta of x minus a. This is how we define actually. Later the integral property we use. Similarly, f of what you call, look at here, r into delta cube of r, that's equal to f of 0 null vector into delta cube of r actually. You should use that property here. E power minus lambda into 0, 0, this equal to 1, this equal to some delta cube only, okay? Some direct delta property. Then again later, that is your what you call rho, epsilon naught should be there here, okay? Rho by epsilon naught. Then integrate that rho, okay, from 0 to infinity, and you will get total charge. That integration, I think that's the integration by parts or some gamma function will come. I hope you can deal with that one. Here you need to do one dot product, r cap by r square dot product with gradient of this one, okay? Do this one. Don't use this one directly, okay? You can use this one, del square v is equal to minus rho by epsilon naught.
Sir.
Wait, 1 second. This one that contain 1 by r square dou by dou r square dou by dou r. Am I right? Is equal to minus rho by epsilon naught. Now you can ask the question, why can't I use this one? No, you will get wrong answer. Because at r equal to 0, this derivative doesn't exist, okay? At r equal to 0, it is going infinity. Don't use this one, okay? Many cases, in many problems, you may need to use this one, but not for this problem. Because look at the function itself, at r equal to 0, derivative doesn't exist. Don't use this one. If you take the, what you call, electric field like this, take this r cap by r square outside, and do like this, I think it will take care about derivative. I mean, that the derivative doesn't exist, that part, it will take care actually, isn't it? Don't do it like this, okay? In this particular problem. It looks very straightforward, isn't it? Here.
Sir,
Yeah, speak out.
after getting rho, I solved by q equals to rho there. I got 0 and
No. You will not get 0. One is Dirac delta, one part. No. The other part, have you integrated 0 to infinity?
yes, sir, 0 till
Yes, 0. 0 is the correct answer. That's correct. 0. 0 is the correct answer. But don't apply this one because this step will not take care that derivative doesn't exist at r equal to 0. Okay, that's why you may get a wrong answer here. Don't apply this one. Do it like this, it will take care of everything. Okay, and separate r cap by r square part, which will give directed. Okay, yes, I think now 2.52, okay, part B, somebody asked, you better to just draw that one on your notes, because it's I better to do that one using some GeoGebra or something, because there comes one equation, am I right? You can write the potential, you can put potential equal to constant, then you will get a surface equation of a surface. Actually, I think using some computational method, if you draw, that would be more convenient. Okay, let me try that one using GeoGebra, or you can take a cross section view. Okay, so that you can just draw that one, just to draw it. Okay, so that if they ask any question, again, they will definitely ask. We are dealing with MCQs, isn't it? Multiple choice question. We should be able to do that one. Okay, just draw it. Mathematics is quite tricky. You should equate that one. You should put potential equal to constant. Am I right? You will have potential as a function of x, y, z, isn't it? You will have v as a function of x, y, z. Wait a second. If you put v naught, what will happen is this equation is some function of x, y, z is equal to constant. Now this is an equation of a surface actually. Now that surface, I think it's quite difficult to argue what kind of surface it is in 3 dimensions. He did that one in the solution manual, but again, you better to draw that one using solution manual in your notes, and just try to remember that one. Okay, because not doable that easily. But it's not a concentric cylinder. Okay, that surface is not a concentric cylinder. Okay, it is it will shift. It's center will shift actually. Yeah, speak out. But surface should be extended to infinity, because charges, look at here, if you see this charge density, you will have some exponential term here. Charge is extending up to infinity, am I right? You have to take surface at infinity. If he asks what is the charge within some finite radius, I think that surface integral would be logical. Okay, would be convenient. Is that okay? But you have to integrate over entire region, and your surface, your radius of your spherical surface, radius will be infinity. Or do that surface integral, put r equal to infinity. Do that finite surface integral with capital R. Okay, by taking one finite surface integral and put that capital R tends to infinity. I hope you may get the right answer. Is that okay? But I hope derivatives are more easier than integral, isn't it? No, later you need to do the integral, obviously, volume integral. Yeah, try that one. You take a that kind of problem is there in exam. Okay, they have given and they have asked what is the electric field. They have given the potential. They asked what is the charge within some radius. Okay, some just problem. But okay, again, you take a sphere of radius, finite radius, capital R, and then put R tends to infinity. Find the charge within the sphere of radius, capital R, then put R tends to infinity. I hope then also you should get 0. Somehow R should come to denominator, and you should, again, if you put R tends to infinity, you will get 0. Okay, you should get it.